Forget tanks, warships, and spy satellites. The fiercest arms race of the 21st century is playing out inside labs colder than Pluto's eyebrows. Here, researchers coax particles into breaking every rule we learned in 5th grade physics, and the result is a brand new kind of computer. Guys, hello, and welcome back to Quantumfy. Today we're tearing open the deceptively simple riddle, how do quantum computers actually work? Stick with me and you'll understand why Google, IBM, and half the world's security agencies are shoveling billions into machines that crash if you sneeze on them, but might one day outthink every classical supercomputer on Earth. Snacks ready? Notifications silenced? Buckle up, let's get started. 1. Quantum reality check, superposition, and entanglement. Classical computers run on bits, tiny switches locked in 0 or 1. Quantum computers upgrade those to qubits, which act more like spinning coins. They can be 0, 1, or any shimmering blend of both at once. That blend is superposition, and it lets one qubit store 2 probability amplitudes instead of a single state. Chain qubits together and the real fun starts. Entanglement. Think of it as cosmic Velcro. Tangle 2 qubits, separate them by a light year, and measure 1, the partner collapses instantly. Einstein called it spooky. Quantum engineers call it bandwidth. Superposition is raw parallelism. Entanglement is the steering wheel. Together, they let algorithms wander through a multiverse of possibilities and slam the brakes where the correct answer hides. Add a third ingredient, interference, and you can cancel wrong paths while amplifying right ones, like noise-canceling headphones that instead of silence leave you with pure signal. Inside the math, each extra qubit doubles state space. 10 qubits, 1024 dimensions, 53, more degrees of freedom than atoms in Earth. That exponential curve is why prototypes with barely 100 qubits already drop jaws. They hint at futures our best classical silicon simply can't touch. And this isn't just about speed, it's about breaking problems that classical computers can't even scratch. Things like modeling quantum materials, decoding complex protein folding, and solving optimization puzzles that could reinvent supply chains or energy grids. When quantum advantage hits, it won't just be faster, it'll be like discovering a new dimension of computing. 2. Qubits in the wild, hardware and decoherence. Magical math is nice until you try to build it. Today's quantum zoo comes in our 4 flagship species: superconducting circuits, Google, IBM, aluminum loops chilled to 15 millikelvin, microwave pulses nudge current clockwise or anti-clockwise encoding 0 and 1, trapped ions, IonQ, quantanium. Individual atoms hover in electromagnetic cages manipulated by laser pokes, slowish gate speeds but coherence measured in seconds, eternity in quantum time. Photonic qubits, PsiQuantum, Xanadu. Information rides on single photons through on-chip waveguides. They run at room temperature, but herding protons is like herding caffeinated cats. Silicon spin qubits, Intel, UNSW. Piggyback on classical chip fabs, storing data in the spin of lone electrons inside silicon quantum dots. All 4 share a supervillain, decoherence, heat, vibration, stray magnetic fields. Any of them can yank a qubit out of superposition in microseconds. That's why quantum rigs resemble alien chandeliers. Multi-stage cryostats, vibration isolation stacks, RF shielding thicker than a bank vault. Current physical error rates hover around 10 to the 3rd power. Spectacularly for physics, brutal for software. Beating decoherence isn't a side quest, it's the boss fight. 3. Playing 4D chess, gates, circuits, and error correction. A classical CPU lives on and not. Quantum processors flex an exotic moveset. Hadamard, H, drops a qubit into perfect 50/50 superposition. Phase gates, STZ, twist the wave function's phase, crucial for interference magic. C0 and CZ entangle pairs, flipping or phase kicking a target qubit only if the control qubit is 1. String thousands of these nanorotations into a quantum circuit. The mission: choreograph constructive interference for right answers, destructive interference for wrong ones. Run the circuit, collapse the qubits via measurement, and statistically the winners pop out on top. But noise stalks every step. Either quantum error correction, QEC, the art of turning fragile divas into a Beyonce-level choir. Today's headline act is the surface code. Park a logical qubit on a 2D sheet of dozens of physical qubits, sprinkle in and chill gorillas that sniff out error syndromes, then feed the pattern into a decoder, often an AI, that flips stragglers back into line every few microseconds. Cross the threshold, 0.1% physical error, and something beautiful happens. Adding more qubits reduces logical error. Google's Willow chip hit that mark in 2024, showing logical fidelity improving as the code grows. Picture a boat that sails faster the heavier it gets. From here, scaling isn't a thought experiment, it's an engineering marathon. Extra bonus: researchers now deploy reinforcement learning agents to optimize microwave pulses, shrinking single qubit errors tenfold and slicing 2-qubit gates times below 100 ns. AI literally teaches qubits kung fu overnight, an essential asset when your tolerance window is shorter than a fruit fly sneeze. 4. From party tricks to payoffs, algorithms, and the NISQ hybrid era. So what does all this wizardry buy us? Shor's algorithm can factor planet-sized integers exponentially faster than classical math. Bye-bye RSA. Grover Search turns a brute force haystack hunt from n steps to the square root of n. On a billion item list, that's a million tries versus just 31,000. Quantum chemistry via VQE or phase estimation promises molecule simulations beyond today's supercomputers. Think enzyme-guided drug design, carbon-negative cement, batteries that embarrass lithium-ion, optimization and ML. QA/OA for logistics routes, quantum kernels that supercharge SVMs, and variational circuits that co-train with GPUs. Early demos already edge out classical baselines on toy datasets. Yet the machines you rent today are NISQ, noisy intermediate scale quantum. They host a few hundred physical qubits, minimal error correction, and a boatload of marketing. Real world value comes from hybrid workflows. Offload the quantum hard kernel to a cloud qubit cluster, let classical silicon chew everything else. Amazon Bracket, Microsoft Azure Quantum, and Google Cloud each sell pay per shot access. One API call dispatches your pulse reschedule. Milliseconds later, a histogram of thousands of bit strings lands in your bucket for classical post-processing. It's messy, jittery, sometimes glorious, and exactly how early GPU clouds felt circa 2010. 5. The stack arms race. Who owns tomorrow? Quantum tech isn't one gadget, it's a 5-layer war. 1. Hardware, qubits, fridges, photonic chips, the shiny tip. 2. Firmware, pulse control, calibration bots, timing electronics. 3. Middleware, real-time decoders, compilers, schedulers mapping Python to picosecond rotations. 4. Algorithm and apps, chemistry suites, crypto killers, supply chain optimizers. 5. Ecosystem, SDKs, standards, training, VC hype, government grants. Google wants the whole pizza. IBM serves an open source buffet. Startups pick gourmet slices. Governments lurk because a working fault-tolerant rig torpedoes today's encryption and rewrites geopolitics. Analysts dubbed Willow's threshold breakthrough the spark of quantum capitalism. Share prices bounced, regulators drafted post-quantum mandates. Message received: whoever tames error correction first sets the tempo of science, finance, and maybe national security for decades. And as the ecosystem grows, expect more abstraction, no-code quantum platforms, drag-and-drop quantum workflows, and open-source quantum dev kits. Just like the classical PC needed Windows and Python to scale, quantum will need its user-friendly moment too. That's when the floodgates truly open. And there you have it. Quantum computing in one adrenaline-laced sprint. Qubits that superpose, entangle, and interfere, hardware that chills to near absolute zero, error correction that turns chaos into choir music, and algorithms poised to upend chemistry, cryptography, logistics, and AI itself. If your brain's spinning faster than a trapped ion qubit, smash that like button. Drop a comment which qubit species will cross the fault-tolerant finish line first. Don't forget to subscribe so you stay quantified. Next episode, we're cracking open post-quantum cryptography, because what good is a quantum beast if your data locks don't evolve too? Until then, keep that curiosity high and your qubits cool. Quantumfy, signing off.